So I want to talk a little bit more about indeterminate forms. In the last video, we saw a couple of examples of limits for different functions. One of those was the limit as x approaches 1 of x squared minus 1 divided by x minus 1. And we saw that when I evaluate this function, right where x is exactly equal to 1, what happens? I get, so when x equals 1, I end up with 0 over 0, which is something that doesn't work, right? And we'll talk about why this doesn't work. But when I look at what happens as the limit approaches 1, so not right at 1, but nearby, we see that this limit turns out to be the number 2. The other example that we looked at last time was as x approaches 0 of sine x over x. Again, we saw that when x is exactly equal to 0, we get the sine of 0, which is 0, divided by x equaling 0 is 0, which is also 0 over 0, which is bad. But when we took this limit was equal to 1. What is this telling us? This is telling us that we can have limits of functions that look like 0 over 0, and we're getting multiple different answers out. Why would that be the case? So here's a little aside. And I'm going to talk about why 0 over 0 is something that's called an indeterminate form. And to do so, let's first look at a regular division problem, something like 8 divided by 4. And we know this is asking the question, if I were to take 8 candies, let's say, and divide them among 4 children, the only possible result is that, well, maybe I should say divide equally among 4 children. If it were, I don't know, some children might want more than others. We see that there's only one result, and that result is 2. And another way to think about this is saying, what is division but the inverse of multiplication? So 4 times what is 8? And there's only one single possible answer to that. The answer is that 4 times 2 is equal to 8, which all of you know. That's sort of boring, Carolyn, right? So let's examine the same thing when we're looking at 0 divided by 0. We see that when we look at 0 divided by 0, this is asking the same question, 0 times what is 0? And just taking a couple of instances from our examples above, we know that, well, 0 times 0 is equal to 0. But it's also the case that 0 times 2 is equal to 0, and 0 times 1 is equal to 0. And in fact, there are an infinite number of values that could work in this place, that there is no single value that satisfies 0 divided by 0. And that's why we call this form indeterminate. It's because we can't determine what the value is. Similarly, let's take a look at some other forms that are indeterminate forms. I'll make a list of them. Indeterminate forms. We just said that 0 over 0 is an indeterminate form. Another form, and I'm going to write it in shorthand, is the idea of infinity divided by infinity. Now, why is this going to be the case? Similarly, we could think of an example of, let's say, the limit as x approaches infinity of x over x. This looks like infinity over infinity, right? And in this case, our infinities are exactly equal to one another. They're exactly equal to x over x, which in this case is actually just going to be 1, right? But let's say that I had different functions that were approaching infinity. For example, if I looked at x approaching infinity of x squared over x, conceptually we can say, aha, that the numerator is getting faster, is approaching infinity. The denominator is approaching infinity, but the infinity in the numerator is approaching infinity much, much faster. It's much bigger than the denominator. And we'll see that this is actually going to approach 0. And I can set up a ratio of functions where both those functions are approaching infinity, but they can approach infinity at different rates, and I can get out any answer I want. That's why we see that this is an indeterminate form. Another couple indeterminate forms are the ideas of infinity minus infinity And again, it's for the same reason as this one above, that when I use this symbol infinity, it's not a single number. It can take on an infinite number of values, and some of those infinities will be bigger or smaller than other infinities. And finally, the weirdest one probably is 0 to the 0 power. In some ways you might say, aha, well, 0 times itself any number of times is always 0, so I would expect this result to be 0. But on the other hand, we also know that anything raised to the 0 power is 1, and really, depending upon the tug and pull between these two values, we see that an infinite number of results can happen from this. So these are all examples of indeterminate forms. I want to contrast that with some examples that are not indeterminate forms. Not indeterminate forms. So a common one that people tend to think that is indeterminate, that isn't, is maybe 0 over infinity. I have infinities, I have zeros, but this is not an indeterminate form, in part because I have something in the denominator and I have 0 in the numerator. It doesn't matter what the denominator is. If my numerator is 0, I'm taking 0 divided by some number, and this can take on any values. This is going to be equal to 0. So for example, if I'm taking the limit as x approaches infinity of 0 over x, it doesn't matter what value of x I plug into here, I'm going to get 0 every single time, and you just get a long rows of 0, 0, 0, 0, 0, 0. Thus, this is not an indeterminate form. Another example, and this is a trickier one that is not an indeterminate form, is the form of 1 over 0. Now this is tricky because this results in a positive or negative infinity. The difference here is that taking on an infinite result is different than taking on any possible result. This is indeterminate because it can take on any number of a million different, not a million, any value that I want it to be, whereas this one can only take on positive or negative infinity. So let's think about why this is the case. This is the case when I think of this fraction. Recall that when I think of the fraction of 8 over 4, I can think of, maybe I have 8 children and each gets 4 candies. Wait, I have 8 candies and each child gets 4 candies. How many children can I pass out the candies to? And we see that if I have 8 candies and each child gets 4 candies, then I can only do that to 2 children, right? Well, let's think of that, a similar analogy of 1 divided by 0, or maybe 8 divided by 0. If I had 8 candies and each child got 0 candies, how many children could I pass the candies out to? Well, I would pass out 0 to the first child and 0 to the second child and 0 to the third child, and you would see that you could do this an infinite number of times, that you could get an infinite number of children would be able to get candies. Also, graphically, we're going to look at this example in a little more detail because it's an important example. Let's think of this as the limit as x approaches 0 of the function 1 over x. When I plug in 0, I see that I get my 1 over 0 results. I can think about this numerically. As my x values get closer and closer to 0, I could maybe try an x value of 1/1000th. And so when I plug that in, I see I get 1 divided by 1/1000th, which simplifies to being 1000. And if I plug in my x value equal to maybe a million, 1/1,000,000th, when I plug that into the function, I get 1 divided by 1 million, which is going to be a million, and we see that as my x values get closer and closer to 0 from the positive side, I'm getting bigger and bigger results. Whereas if I approach from the negative side, let's say I approach with negative 1,000th, I get 1 divided by negative 1,000, which gives me negative 1,000. And I can see analogously that I would get closer and closer to negative infinity. And graphically, this function, the 1 over x function, is a rational function, and I have a vertical asymptote right at x equals 0. And the function looks something like this and something like this. So as I approach 0 from the right-hand side, we see that my values are getting bigger and bigger and bigger, and as I approach 0 from the left-hand side, my values are getting more and more and more negative. So that's just a brief theoretical overview of some indeterminate forms. The next topic that I want to talk about is evaluating limits from graphs. So let's say that I don't have a function, that all I'm given is this graph here, and this is a crazy graph, right? I tried to make a crazy graph so it would be hard to evaluate the limits on it. This graph is a piecewise graph. It starts out by going in a straight line with an x-coordinate of -4 and a y-coordinate of 2 down to -2, 0, and then we have this arcing piece through here, but right at x equals 0 there's a hole in the graph that's denoted by this empty circle, and instead of having a value right there, the function takes on a value way up here. It's a discontinuity that's up there, and then the end of the graph is this piece out here, and notice that there's a hole here and there's no function defined right where x equals 3. So what we're going to look at is just using this graph, we want to find the limit at various places, both the right and the left-hand limits. And something that we're going to keep in mind is that the limit exists when both the left and the right limit agree, and it doesn't matter what's going on right at that point. So right at x equals 0, it doesn't matter that the function is way up here. We only want to know what's happening with the right and the left. So let's take a look. Our first limit that we're asked to look at is when x approaches -3, and so because there's no positive or negative up here, it means that I want to compare x going to -3 from both the right side and the left side. So let's look at the graph. X equals -3 is right here, and my functional values, let's say this point on the graph is about where y equals 1, and I see that as I approach from the left-hand side, moving this way, my y values are approaching +1. That means that my limit as I approach from the negative side of -3 is 1, and when I approach from the positive side, or from the right, I'm also approaching a y value of 1. That means that both the left-hand limit and the right-hand limit agree, and they both agree at the value of 1. The next one that we're looking at is when x approaches 0, and again I'm going to have to look from the left side as well as the right side, and as I approach from the left over here, I see that we're approaching a value of about 1.4, and as I approach from this side, the right-hand limit agrees with the left-hand limit, and they're both approaching a y value of about 1.4. I'm guessing that's about what the height on this graph is. So I'm going to say that both the left-hand limit and the right-hand limits agree, and they're both approaching the same place, which is about 1.4, which is my y value. Finally, let's look at the limit as x approaches -2. So in this case, as I approach -2 from the left-hand side, we see that we're traveling along this straight line, and it's approaching 0 down here. Whereas when I approach from the right-hand side, I'm not approaching on the straight line anymore. I'm approaching along this curved line, and it's approaching y equals 0. But it doesn't matter that this is a straight line and this is a curved line. Both of them are lining up to approach the exact same point, the point where y equals 0. So in this case, both the left-hand limit and the right-hand limit agree, and they're both approaching y equals 0. So that way the limit of my function is 0. This is written out a little more explicitly. Let's look at when x approaches 2 from the positive side. So in this case, that's going to be my right-hand limit. Here's where 2 is. On my function, that means I'm walking along this direction. And as I step this way, my y values are all approaching the same value of 2. So I know that my right-hand limit in this case is 2. My left-hand limit, on the other hand, as I approach x equals 2, I'm down here along this curve. My y values are approaching 0. And so here I'm asking, what's my limit as x approaches 2? I see that my right-hand limit and my left-hand limit don't agree. And so this limit does not exist. That limit does not exist.